So today we're going to be looking at a number of different ways that we can prove that a quadrilateral is a parallelogram. And basically what this means is we're going to prove that our quadrilateral fits the definition of what a parallelogram is, meaning that it has two pairs of opposite sides that are parallel to each other. So that's kind of the name of the game here, looking at a quadrilateral and saying, hey, how can I show that the opposite sides are parallel in that shape? So let's go ahead and take a look at the first way we're going to do that. And that's going to be using this theorem, which is actually the converse of a theorem that we learned previously. Remember, we learned a theorem previously that says if a parallelogram is a quadrilateral, if a quadrilateral is a parallelogram, then its opposite sides, both pairs of opposite sides, will be congruent, right? So this is the converse of that, meaning that we're going to take that statement and we're going to switch it around. Instead of saying if it's a parallelogram, then its opposite sides are congruent, we're going to say that if its opposite sides are congruent, then it must be a parallelogram. And so that's like the first way that we can prove that something has to be a parallelogram, is we can look at it and we can see, hey, look, these opposite sides are congruent and these opposite sides are congruent. That means it must be a parallelogram. But what I want to do is I want to show why this works. I'm going to prove that this theorem will always be true. So bear with me a second here. We're going to look at this shape and we're going to say, all right, if I know that these opposite sides are congruent and these opposite sides are congruent, how does that make the opposite sides also have to be parallel? And to do that, the first thing is we're going to add in a diagonal. And it doesn't technically matter which diagonal I draw, so I'll just go ahead and draw this diagonal right there. And in drawing that diagonal, I've created two triangles. And these two triangles, I'll notice, both have this side in them, they both have this side in them, and then they share this blue side, the diagonal. So that means that our triangles are congruent by SSS. Now to make this a little bit easier, let's label some of these points so I can kind of write out my reasoning here. I'm going to say that triangle ABC is congruent to triangle CDA by SSS. Now, if those two triangles are congruent by SSS, the next thing we can do is we can say, oh, look, that means that this angle here and this angle there are congruent by, because the corresponding parts of our congruent triangles have to be congruent. So this angle and this angle are corresponding parts of these. Once we say that the triangles are congruent, we know all their parts have matches on each other, so this matches that, and they're congruent to each other. So we can say that those two angles are congruent. So we'll say angle BAC is congruent to angle DCA. And the reason for that is what we call CPCTC, which again stands for corresponding parts of congruent triangles are congruent. And that means that if these two angles are congruent, well, look, they're alternate interior angles. And we learned a while back that if I have two lines, right, like segment AB and segment CD, crossed by a transversal, like segment AC, and these alternate interior angles are congruent, it means that those two lines must be parallel. So that would tell us that segment AB is parallel to segment DC. All right, so we've proven now that one of our sets of opposite sides are parallel, but we can actually go ahead and use the same reasoning. We can say that this angle here and this angle here are also congruent by CPCTC. So I'm actually going to just kind of add to my statement. I'm going to say angle DAC is congruent to angle BCA, and the other two angles are congruent because of CPCTC. So I've said that these two angles are congruent as well as these two. And so that means that not only is segment AB parallel to DC, but it also means that segment AD has to be parallel to segment BC. So we can say and segment AD is parallel to segment BC. And so now you can see we've shown that both pairs of opposite sides are parallel, which means that our quadrilateral must be a parallelogram. So that was the first way we can prove that a quadrilateral has to be a parallelogram. The second way is if we look at it and we say, hey, I have an angle, like say angle A right here, And if I add A and B together, I get 180. And if I add A and D together, I get 180. That means this has to be a parallelogram. So if one angle of the quadrilateral is supplementary to both of its consecutive angles, then it has to be a parallelogram. Well, let's prove why that works. Let's look over here at my other quadrilateral. I've numbered these angles instead of using the letters at the vertices. I've just numbered them 1, 2, and 3. If I know that angles 1 and 3 add up to 180, and I know angles 1 and 2 add up to 180, why does that make the opposite sides have to be parallel? Why does it make it fit the definition of a parallelogram? Well, I'll say this. If the measure of angle 1 plus the measure of angle 3 equals 180, I guess I should put some letters again on here, A, B, C, and D. If those two add up to 180, then that means that AD is parallel to BC because the same side interior angles are supplementary. We're going back to an idea that we learned a while back that says, hey, if these two angles, which are same side interiors, if they're supplementary, then this line and this line have to be parallel to each other. So again, we've now proven that this is parallel to this because angles 1 and 3 add up to 180. But then we could also do the same reasoning with angles 1 and 2. If the measure of angle 1 plus the measure of angle 2 equals 180, then that would mean that segment AB is parallel to segment DC because, again, the same side interior angles are now supplementary. And so if these two sides, this one and this one, are parallel, now we've proven that this is a parallelogram because both pairs of opposite sides are parallel. And again, this is going off the idea that angle 1 was supplementary to both of its consecutive angles, 3 and 2. So that's the second way we can prove that our quadrilateral might be a parallelogram. And so that takes us to our third way. And the third way we can prove that our quadrilateral has to be a parallelogram is if we can see that both pairs of opposite angles are congruent. So if these two are both x degrees and these two are both y degrees, it means that this has to be a parallelogram. Or in this picture, if A is congruent to C and angle B is congruent to angle D, it's got to be a parallelogram. So let's think about why this one works. Well, first of all, you'll notice I put x and x and y as our two angle measures in this picture. So again, we're assuming, hey, we know that these two angles are both the same and we know these two angles are both the same number of degrees. Well, it's a quadrilateral. So what that would indicate is that if I take x plus y, I have to get 360, right? Because in my quadrilateral, my four-sided shape, those interior angles have to add up to 4 minus 2 times 180, which is 2 times 180, which is going to be 360, right? So our interior angles have to add up to 360 in this picture. Now if I combine my like terms here, it's going to give me 2x plus 2y equals 360. And now what I'm going to do is I'm going to divide every term in this equation by 2. I'm going to divide that and that and that all by 2. And that tells me that x plus y now equals 180. And let's look at what that implies. If I take this x and I add it to this one, x plus y, it says it has to equal 180. And since those are, again, same side interior angles, then it tells me that this and this are parallel because these same side interior angles or these same side interior angles are adding up to 180. They're supplementary. But then if I say this x plus this y equals 180 or this x plus this y equals 180, that tells me that these two segments have to be parallel. So now you can see we've proven that based on these two angles being x and these two angles being y, we can show that now these opposite sides are parallel and these opposite sides are parallel, so this has to be a parallelogram. And now the fourth way that we can prove that a quadrilateral is a parallelogram is if we are given information that says that the diagonals are bisecting each other. So if you look at this picture here, if we knew that segment AX and segment XC were congruent, let's go ahead and mark that in our picture. If we knew that those are congruent and that segment BX and segment XD are congruent, That would show us that these diagonals are cutting each other in half. They're bisecting each other. That makes it so that this shape has to be a parallelogram. So let's talk about why. Again, I'm going to label my four corners as A, B, C, and D, and then I'm going to label that point there where these diagonals are intersecting as point E. And you can see I've drawn it so that my diagonals are bisecting each other. So the question is, how does that make the opposite sides have to be parallel to each other? Well, we're going to use the idea of congruent triangles again. I'm going to mark my vertical angles congruent here in the middle. So those two angles are congruent because they're vertical angles, and then that angle and that angle are congruent because they're vertical angles. And so I'm not going to write this one out. I'm just going to walk you through this one. I can now see that this triangle here, triangle AED, and this triangle over here, triangle CEB, they're congruent because of side, angle, side congruence. Two pairs of sides congruent, and the included angles are congruent. And since these two triangles are congruent, it would indicate that this angle here and this angle here are congruent because they're corresponding parts. And if those angles are congruent, they're also, I notice, alternate interior angles for this line and this line crossed by this transversal. So these alternate interior angles that are congruent makes this and this parallel. And now we can use the same logic for these other two triangles. We can see that they're congruent by side, angle, side, side, angle, side. And that would mean that, let's say, this angle and this angle are congruent because they're corresponding parts of these two congruent triangles. They're also alternate interior angles for this segment and this segment crossed by this transversal. So they're going to be parallel. And now again, you can see that we've demonstrated, based on the fact that the diagonals were cutting each other into two congruent parts, they were bisecting each other, that led us to be able to say that their opposite sides of this parallelogram were parallel, and that makes it a parallelogram. So we have one more way that we're going to look at, and let's take a look at that now. Okay, so this final way of proving a parallelogram, or proving that a quadrilateral is a parallelogram, is actually, you'll notice, not one of the converses of an earlier theorem. This is something that's a little bit new that we haven't talked about. This one says that if I have one pair of my sides, one pair of opposite sides, and I know two things. I know that they are congruent to each other and parallel to each other, then it means that the shape must be a parallelogram. And so you can see, again, the game that we're trying to play here is trying to figure out, why does this information prove that both pairs of opposite sides are parallel? Why does it prove that my shape fits the definition of a parallelogram? And if that's our game, we can see we're actually halfway there, because we already have, based on kind of the setup for the problem, like what we would call the given information, we already have that one pair of the opposite sides are parallel. So the question is, how do we prove that this information gives the other pair of opposite sides as parallel as well? And so what we're going to do is we are going to draw in one of the diagonals again. So I'm going to draw in this diagonal right here. And once again, I should label my corners, A, B, C, and D. And what I'll notice is that in my picture now, I have this pair of angles that has to be congruent, because again, they're alternate interior angles. I have my parallel lines as BC and AD. My transversal here is AC. These are alternate interior angles. That means they have to be congruent since the lines are parallel. But I also could go ahead and throw a mark on segment AC and say that it's kind of congruent to itself, right? And that would indicate that these two triangles are congruent, again, by side, angle, side. Side, angle, side. So again, I have a pair of congruent triangles. That would indicate, that would mean that this angle and this angle are now congruent because they're corresponding parts of these now congruent triangles. They're corresponding parts, and all the corresponding parts of my congruent triangles have to be congruent. So since those angles are congruent, that forces us to be able to say segment AB and segment CD must be parallel, because these alternate interior angles, well, they're congruent to each other. So that means that this and this are now parallel, and you can see we have now both pairs of opposite sides parallel. So it must be a parallelogram. So those are our 5 different ways that we can prove that a quadrilateral is a parallelogram. 4 of them are based on converses of previously learned theorems, and then we have this final one here that's kind of a bit of a new one, saying, hey, if we know 2 things about one pair of opposite sides, we can prove that this shape must be a parallelogram.